Well, hello again. I'm Elif, and this is Danny. And we're from the AndroidX Jetpack team at Google. And today, we're going to talk to you about how you can keep tabs on your data using our libraries, Room and DataStore on the web.
Ooh.
So before we get started and dive in, here's a little bit of a rundown of our agenda today. So we're going to kick off with why you want to use storage on the web in the first place, followed up with what web storage options you have out there right now, what all this means for Kotlin and KMP on the web, and then we're going to talk about our AndroidX web solutions with DataStore and Room, and wrap up with key takeaways. So when we say web storage, the first thing that might pop into your head might be cookies. And although that sounds like a fair assumption and sounds kind of delicious, no, we're not talking about cookies. Cookies are server-driven, and what we're talking about today is local client-side storage and web storage that lives completely in the user's browser. So this is the kind of storage that allows amazing things like the Chrome Dino game to exist and run completely offline in your browser. So in today's age of let's just store everything in the cloud, why would you might be wondering why you would want to use storage on the web in the first place. Well, if you want apps that load instantly, you can use this as a cache. You can also let your apps use web storage to run completely offline. And if you have an amount of large content that you want to store and manage, this would be a good choice. So what kind of web storage options do we have out right now? Well, it kind of depends on what your use case is. And if you have a smaller data use case, then you can use session storage or local storage. These are essentially quick and easy key value pair storage solutions for doing things like saving a dark mode preference. Next up, in the middle tier, we have IndexedDB, which handles structured JSON objects and is great for things like caching. But when you want a large performance storage solution, that's where Origin Private File System comes in, short for OPFS. And spoiler alert, this is what we used to make relational databases like Room work in the browser. So crucially, we should mention that regardless of which one of these that you select, they all follow what is referred to as the same origin policy. So what does this mean? Basically, this means that a database created by an app on the browser in one origin is sandboxed to that origin. And this means that this database is invisible and inaccessible to anything that doesn't share that same origin. For example, here we have mail.google.com/inbox. Let's say you create a database there. Then this would be accessible to mail.google.com/sent, but it won't be accessible to maps.google.com because they don't share the same origin. And that's essentially what we mean by that. So coming back to the web storage APIs, let's do a little bit of a deep dive on each of them, and we'll get started with the smaller built-in browser APIs, session storage and local storage. As I just mentioned, these two are these two are used for storing key value pairs, and they are perfect for lightweight utilities like saving a user's theme preferences. So in fact, local storage out of these two is how the Chrome Dino game from earlier keeps track of your personal best scores, even though you play that game exclusively offline. The size of the data, as I mentioned earlier, needs to be a little small. And the reason for this is because these two are synchronous APIs, which means that they can block the main thread and cause your app UI to literally freeze. So next up, we'll have IndexedDB, and Danny will talk about that.
So IndexedDB, so Elif mentioned local essential storage, session storage, those are key value pairs. IndexedDB is like that one in the middle. It's kind of like an pretty old technology, but it's pretty useful in the web browser. It's been there for a while. Essentially, it allows you to store JSON objects, and it's a NoSQL database, and I'll try to explain that in a little bit. But it's really good as a cache, for example, because if you get HTTP requests that are in JSON format, you can go ahead and put them straight into that database. It can actually also store good size files. and it integrates well with the web APIs, specifically like if you put a upload button, and you upload a file, you get a file type, and you can put that straight into the IndexedDB. So that's kind of nice. And then different from the local in-session storage, the APIs are asynchronous, so that means it doesn't block the main thread, and that's good to keep the UI reactive. Now, it does have a few limitations, especially it is not a full-fledged relational database, as you can imagine, and so what you can search is a little bit limited, and there's some nuance to it on how the space is managed. It can be reclaimed by the browser, and this depends on the browser implementation. But let's go back to that NoSQL part of IndexedDB. If you're familiar with relational databases, you might not be familiar with NoSQL, but I'll try to briefly explain it. Imagine we're storing cats, information about cats. Here we have 2 cats, Tom and Pelusa. They're my kitties. And they have an ID, a name, and an age. You create an object store, but one important thing is you have to create a key on one of the properties. And in this case, I use ID. And what this basically means is I can get all the objects at once, or I can get a specific one based on that exact match. There's really no searching. You could create other indexes, though, and this is the index part, I guess, from the name. We could create one for name so that we can search by name, but it's not really searching. Again, you have to provide an exact match. And that's fine. Imagine things got a little bit more complicated, and I know I said it's not a relational database, but if we were to try and create some relationships, it becomes complicated because we need 3 different object store, and the only way to actually join these or relate to them is by querying them separately and then doing it at code. It's not quite as a relational database. But it's still pretty powerful, and that's kind of not the way it's meant to be used. The idea is you actually structure your JSON object to sort of contain these relationships. So if we were to use it in a more NoSQL way, what would happen is we would have a JSON object that has like the owner, and then the cats are like a list. And so it represents one-to-many relationships, but it's still not really good for many-to-many. All right, that was IndexedDB. What is Origin Private File System? So it's a very different one from the ones we mentioned before. It's really a virtual file system, and it allows you to store files and directories, and it looks like a regular file system in the sense that you can create directory hierarchies, and whatever the files are just binaries, you can store whatever you want. Now, the cool thing about it, different from IndexedDB, is that you can have byte-level access. And imagine you have a local web player for whatever reason. You have a 3-hour DJ mix, and you want to seek to the hour and 30 minutes. Doing that with IndexedDB is a bit hard because you have to load the whole file. But with something like OPFS, you can seek to a specific position and start reading from there. It does have asynchronous APIs, too, that you could use it from the main thread. But that's kind of not the best way to use it. It has a synchronous API that's really performant, but you can use it on a worker thread, on a web worker. And we'll try to explain this a little bit later. But that's kind of like the best way to use OPFS. How do we use these things from Kotlin? Elif will tell you.
Yes. Now let's talk about KMP and what it means to have KMP on the web, I guess, and these storage solutions. So session storage, local storage, IndexedDB, and OPFS are all browser APIs, and they're not a part of the Kotlin standard library for web targets. This means that we are required to either use interoperability with Kotlin externals, or we can also opt to use the Kotlin X browser library, which has already declared interops for some of these, which we'll go into in a bit. And we should also mention that Kotlin X browser library is currently a work in progress library, so the actual API surface is subject to change. So a very direct example of how you can use the Kotlin X browser APIs out of the box is with local storage. So how you do this is you can simply get a local storage instance from the Kotlin X browser library, and you can set or get your data or values. Pretty straightforward. Things get a little bit more complicated when you try to do this with IndexedDB. So IndexedDB doesn't have any out-of-the-box APIs that are shipped from Kotlin X browser. This means that we need to do the external declarations that I just mentioned for interoperability. So how we do this, in this case, is we get an index DB from the window, which will allow us to open a database. And we need to mention that because these APIs are asynchronous, when we call open, we get a request to open the database, which means that we have to hook a callback, which is going to, once invoked, going to allow us to create an instance of this database. So here's an example that we can run through on how you would do this, where we create a database in which we're going to store some cats. So we first install a callback, as I mentioned, that once invoked, it will start a transaction. And it will loop through the database and read all the cat entries. One important thing to note here is that because this is a callback-based asynchronous API, it's going to become very complex and verbose if we were to do relationships in this scenario. Without writing any utility functions, think of like the relationships that Danny mentioned between like an owner and a cat. And it will essentially become what we call a callback hell, which sounds horrible and we don't want to be in. So there's a similar story with OPFS, where there isn't any APIs that are shipped out of the box, and we also need to use external declarations. But the difference here is that because it's a more modern asynchronous API, it's actually based on promises, and we can leverage language features to handle these asynchronous operations. So for JavaScript, this is the async operator, and for Kotlin, this is coroutines. And if we walk through a small example, here's an example where we write into OPFS, and because, again, the API is promise-based, we bridge through Kotlin coroutines, and specifically the await extension function. So let's say you have a file that contains a list of cats, and you want to add a cat named Tom to it. Well, you would first need to get the OPFS root, open the file, and get a writable object, which is then used to write the content of the file. And once the promise finishes from the right call, then the data is successfully written. So as we've seen in these previous recent slides, these APIs are not very straightforward to use directly. And on top of that, all the code that we just looked at is for the web target only. So this is exactly why we went into the whole effort of adding our libraries, to adding support for web on our libraries, because we believe that storage logic is very close to your business logic, and therefore it's definitely something that you want to share across different platforms. And for this reason, we wrapped these low-level target-specific APIs inside the familiar AndroidX libraries that we have, and this lets you write your persistence code just once in KMP Common Code and compile seamlessly for mobile, desktop, and the browser. There we go. And let's talk about this specifically regarding what we did in the libraries and kick off with DataStore. So if you're not familiar with DataStore, oh, you need some reminding. DataStore is an AndroidX library storing key value pairs in applications, and it uses Kotlin flows and coroutines for asynchronous data access. Setting it up is quite straightforward. You can use a DataStore. You can create a DataStore using the DataStore factory to get an instance, and all you need to do is pass a serializer, which is going to handle reading and writing your data models, background coroutine scope, and a file producer lambda. And once initialized, consuming your data is completely reactive, as I mentioned before. You can map your data layer to a Kotlin flow, and whenever a write happens, your app instantly receives the updated state. So after that quick refresher, let's now finally talk about DataStore on the web. Because DataStore, as I mentioned, is conceptually a key value store, it actually maps really well for web's native session and local storage. And on top of this, it also works well with OPFS using external declarations because OPFS has asynchronous APIs, and we can leverage Kotlin coroutines to bridge this gap. So initializing a DataStore for the web, just as straightforward. All you need to do is provide the specific web storage that you need for your use case. In this example, we have a web local storage, but you have the option to do a web session storage or a web OPFS storage. And you need to pass in a web serializer, which we ship out of the box, or you can also provide your custom OQO serializer. So the one last thing, and it was the biggest challenge that we faced in this endeavor, is that one of the best features of DataStore is the flow observability. So this means that if your data changes in one part of your app, then the rest of the app is able to react instantly. On the web, this maps to cross-tab communication, or making this work across multiple tabs. For local storage, the browser actually makes this very straightforward and easy for us, and it has a built-in storage event that gets fired whenever a tab changes the data, and it's used to notify the other tab. But because OPFS is a file system, it doesn't natively broadcast these file changes. And this means that we had to implement a custom under-the-hood solution for this. And we can walk through an example of what that means so that we can understand it a little bit more directly. So let's say you have these two tabs. Both are using DataStore backed by a local storage, and tab A updates the theme to dark mode. What happens here is DataStore writes this key value pair to the local storage. And because this is the standard web API local storage, the browser does the heavy lifting and fires a storage event, which tab B is already listening for. Tab B's listener receives the storage event and triggers a reread, and the flow emits a new state. And just like that, the UI in tab B is updated. So I mentioned that OPFS did not support this out of the box or give us any kind of storage event-like solution. And we had to solve this by implementing a broadcast channel notification mechanism, which essentially solves the problem for OPFS in a similar way. So in this case, why did we do this? Well, to ensure that no matter if you're using local storage or OPFS, your app will feel reactive and synchronized everywhere.
Cool. So that was DataStore. I'll go into Room now, and similarly for the web. So Room, if you don't know anything about it, it is our AndroidX library that makes it really easy to use SQLite databases on your application. And the core thing about it is that it's an annotation API, and we generate code. So let's go to a refresher. It's a relational database, SQLite. And so if you want to create a table, you create a data class, annotate it with an entity. The properties on this class is going to be the columns on those tables. Now, if you want to do operations on that database, you create an interface, and we call these data access objects. And in here, you define the kind of operations you can do, like a write, for example, again, using annotation API at insert. And then if you want a query, then you use the query annotation. And the cool thing here is that you write your SQL query itself. So Room allows you to leverage the SQL language itself. So this is a simple query. It can be recursive. It can be joins. It can get really complicated. Now, the glue to all of these things is just an abstract class that you annotate with database. And once Room sees this, it then generates the code. Now, on the runtime side of things, when you want to build a database, you use a Room database builder. We set a driver here, and that's the lower layer, a bundle SQLite driver. And then once you have a database instance, you can start using it. Pretty neat. Now, Room originally was created for Android a bunch of years ago. And 2 years ago, we actually announced its support for iOS and desktop. So we converted what you know as Room 2.0 to KMP. And I'm happy to announce now that Room supports web and the JavaScript and WASM.js targets. But the Room that supports the web is actually Room 3.0. And it might not be the 2.0 that you think it is. It is a new API breaking changes version that we did, and it only supports Kotlin symbol processor. It only generates Kotlin code. It has coroutine APIs as its API surface mainly, and then it was made also for the web. So it supports asynchronous web APIs, and specifically at the lower layer, it uses a web worker driver. Now you might be wondering, oh, what is this Room 3.0? Why did you have to do it, or why did you even took so long to support web? Well, There's a few reasons, but we wanted to do a major breaking version. One was for the sake of the project, for long-term maintainability. Room 2.0 supported many combination of setups of environment. It generated Java code, supported KPT, supported Java annotation processor. So you can imagine that being complicated. The other big thing we did in Room 3.0 was drop the Android support SQLite APIs. These were really kind of holding the library back, and instead we opted to use the SQLite driver APIs, which were made from the beginning for KMP. But we know it can be really hard to migrate to the new driver API, so we do have a backwards compatible layer and artifact. And then the other big thing is Room internally. Again, it was made in Android, actually before Kotlin. It was like a Java library. Its internals were all synchronous. And to make it support the web, we had to convert them to be asynchronous and using coroutines API. And I want to emphasize this because it is actually what made this project kind of take a lot of time and made it quite hard. And so I'll try to explain exactly what I mean by that. But before we go in there, let's take a look at that lower layer. Room uses the SQLite driver APIs, and that's what empowers Room. And I'll show you a little bit of code of what these APIs look like, so you get a sense of what it is. In essence, they mimic the C SQLite API, and the way you use this is you create a driver, you open a database that gives you a connection. The connection is what you start to operate on the database. You can execute a statement, like create a table here. If you want to insert something, for example, you can prepare a query and insert. And to pass runtime values, you bind values to that statement. And then to get something back, you also prepare a different statement, a select one, and you iterate on that statement via the step function. The key thing to notice here is that the key functions here are step, prepare, and open. And you can use this on a standalone app, but Room uses this, and it's really what empowers Room. And when we made these APIs, originally we made them thinking in KMP and the different platform we were to support. So we actually have what is the common code. It's an expect interface. And then for non-web, we have those same common functionality, but then those key APIs, like prepare, is a synchronous blocking function, because the underlying SQLite C library will be blocking. But on the web, these interfaces are asynchronous, because on the web, as you saw, IndexedDB and OPFS specifically are asynchronous. And if you use a web worker, they're going to be asynchronous. And this might be weird, but this is exactly how we would like you to use this interface. If you have common code that doesn't target web, the most efficient way to use Room and SQLite is through blocking functions. But if you are targeting web, then you have to use a synchronous function. So you may be wondering, oh, but what do I do with my common code that needs to support all platforms, including web? Well, for this, we created a new artifact called SQLite Async, and this has these extension functions that are suspend functions, because the suspend functions are the functions that can work on all the platform. And it might be weird that this is an opt-in, an artifact that you have to add, and discoverability is not great, but it's on purpose. We do want you to make that big decision that if you're going to write common code at this low level, that you will have to use this async APIs. And for non-web specifically, there might be some penalty or overhead. Cool. So as you saw, SQLite drivers, they have async APIs. And if we wanted to use these async APIs in common code, if we want to use SQLite in common code that targets web and non-web, we have to use async API. And this leads to what I call a coloring problem, or what might be referred as a coloring problem. And to explain this, think when you write a function in Kotlin, you actually have to decide on something. You might not think about it too much, but you actually paint the function. And specifically, the difference is between painting blocking functions and asynchronous functions, or suspend functions versus non-suspend. And we can say blocking functions are red, we can say suspend functions are blue. And the problem here is the asymmetry between these two. As you know, or might not know, blue functions can call other blue functions and red functions, but red functions cannot call blue functions. And I didn't invent this. This was thought about. It's a problem that's in other languages, and it's well explained by a blog post by Bob Nystrom called What Color is Your Function? Because this is a problem that doesn't only exist in Kotlin. Other languages have this issue, like JavaScript with a sync keyword, Dart, I believe, C#. They kind of have similar, or they kind of run into the same problem because of the async language feature. So how does this relate to Room? So imagine that now you do a database operation in Room 2.0, before we had web. At the top of it, we have cat DAO, and at the bottom, as you keep going, we have a bunch of internal functions, and all the way at the bottom, you can see we use the SQLite driver APIs. Now, the truth is that these were all red functions, right? But if we want to support web, we have to change that lower layer into a blue function. But now we run into an issue. Red functions cannot call blue functions, right? So what are we supposed to do? Oh, easy. We slap a run blocking in there. Don't do that. Bad idea. And this really oversimplifies the problem. That configure doesn't only call prepare. This prepare gets used in many places, and all these functions are called from other different locations. So that's not the right solution. What we needed to do was actually go ahead and repaint Room internal into coroutines and into blue functions. And you can imagine doing this in a behavior consistent way and efficient way was not an easy task. But many good things came out of this. Room 3.0, its internals are now in coroutines. That means the connection pool is now coroutine based. So Room uses multiple connections to enable parallelism. And when you run out of connections to do database operations, it used to block the thread, but now it'll actually suspend. That's really nice. Similar to DataStore, Room also has like an observable API, so we were able to convert that to be flow-based, which is nice, easier cancellation, call by default. And then on the API side of things, we have some callbacks. These were upgraded or migrated to be suspend, and enabling to use those lower level APIs if you needed to, but this was a API breaking chain, which is another reason why we had to do this major breaking version. But it's really nice because then Room 3.0 is really Kotlin Multiplatform. Once you figure out the database path, which is really the platform-specific thing, everything else is common code. Your configuration can be written in common code, your migration is in common code, and your database operations are in common code. And I have to emphasize that we really believe and value that you can use Room on your common code because Room being at that data layer of your business logic is really something that you basically want to share across your platforms. Cool, so that was Room for the web. That lower layer, there's one missing piece of it on our story here to support web, and it's the web worker driver. So in order to support Room for the web, we had to also work on that lower layer. So if you were to use Room for the web, similar code that we saw before, you start with a database builder, but this time in the set driver, you create a web worker driver. And what this is we have an API called web worker SQLite driver, where you use this API that we created, but you give it your own worker for now. And the idea is that this web worker will communicate, this web worker driver will communicate with a worker to do the database operations. So I know I mentioned what a web worker is. Now it's finally time to explain it. What exactly is it? It is a web technology. It is something that runs on a background thread in the browser. So the browser has the main thread where the UI is and rendering is done. And it has background threads, but the way to run things there is through a web worker. But the thing is, it runs a script. It runs a JavaScript file or script. It doesn't run like Kotlin code. And that's kind of like the major difference between the normal background thread. In Kotlin, when you start a new thread, in the JVM at least, you can capture local variables, or you can run a function that's in the same file. Not with web workers. The code is really isolated, and it doesn't really share memory. It does, but the memory is just different. You have to use a message passing system. And so they're kind of hard to use, and Kotlin and JetBrains kind of knows this, and there's even a Keep proposal to try to make them better. But it's a bit old, it hasn't gotten a lot of traction, and it's still something that's being figured out. Now, I mentioned a web worker is something, it's a script that runs and starts on a background thread. So we have what we call a main thread and a worker thread. And how do the two exactly communicate and how do they work in terms of database operations in Room? Well, what we did was we basically implemented a driver that bridges into the worker. And as long as they talk in a small messaging protocol, they'll be able to do things together. And so imagine we wanted to open a database. What the main thread side of things do, or the driver side, is they send a small message that says, hey, I have a request, it's a command, it's an open, and here are the arguments, which in this case would be just the name of the database. And what the web worker does is it just responds, it opens the database and responds back, hey, I open your database, by the way, this is the ID, you're gonna use that later. And then on a follow-up request, we now do a prepare, right? So we're using those key SQLite driver APIs, open, prepare, and step. In this case, we send them a payload that's to prepare. We give it the database ID, the one that it gave us on an earlier message, and then we give it the SQL we want it to prepare, right? And it goes ahead and does that, and it prepares that statement, responding back, here's the ID to it, and here's some meta information about it. Name of the columns, how many parameters it has. Thanks to this messaging protocol, we were able to then implement the web worker driver. On the main side of things, we have the SQLite driver interfaces that what Room uses or you would use. Internally, it has a coroutine bridging logic to do this message passing, and it figures out the handles, the type conversions. And then the web worker side is just a JavaScript file that understands that communication protocol. That's very simple. It just has those three main messages, prepare, step, and open. And then how it actually performs this operation is kind of open. Like you can use SQLite WASM, which is the official SQLite project that compiles SQLite for WASM, or you can use like another JavaScript library like SQL.js. That's kind of the cool thing about it. Because you provide the web worker, you can build it however you want. But we know that can be a bit hard, so we do have some web worker implementations already, specifically one that uses SQLite WASM, and SQL.js. They're on this GitHub. And on a future, we do hope to improve this and have these web workers be on possibly NPM or somewhere easier to access. But right now, you have to kind of copy them into your project and serve them as part of your web app. Cool, that was Room.
Yes, and to wrap up, so what are our key takeaways from today's session? Well, Room and DataStore now fully support web targets with stable releases coming soon, and now you can share your persistence layer across Android, iOS, and the web. Thank you for joining us this morning, and we hope you have a great rest of your conference.
So if we want to take we can take questions, and if you have questions to ask us, or if you have nice things to say, we'll take those, or bad things. But there's a microphone in the middle, so if you have a question, please stand up, say on the microphone, and we'll happily answer it. Otherwise, enjoy the rest of your conference. Yes,
I think so,
please.
yeah, unfortunately.
It's so that it gets recorded and transmitted, and everybody can see it, even your grandma.
Just like your persistence layer, shared across all platforms.
Yes.
I know.
Ladies and gentlemen, this is TJ with a question.
Hello. So I have a question about IndexedDB with Room for Web. You had mentioned earlier that IndexedDB is NoSQL, and Room, the APIs are mostly SQL, and there's stuff like transactions and stuff. Was it kind of, can you expect like all the behaviors you expect from a regular SQL transaction to work just as well as web? Are there any gotchas you should be aware about? Are there any APIs that you'd expect from SQL but don't quite match up from web, or you can just expect that it'll work, everything should just work fine?
Yes, great question. So Room for the web doesn't use IndexedDB.
Oh, okay.
So that's easy problem solved, right? We actually use OPFS and we save the file, the database file, in OPFS, and then we use SQLite, the library, whether it might be SQLite WASM or SQLite.js, to then talk to that database. And because it's relational, we basically sidestep all the differences between IndexedDB and a relational database. So in summary, Room for the web does not use IndexedDB. It is an option of web storage that you can use, a bit hard because you have to use external declarations. But otherwise, we don't really use it in neither DataStore or Room. But
Gotcha.
it is an option.
Gotcha. Thanks.
You're welcome. Any other hard questions?
Oh.
Ian.
Yeah, I had a question about local storage versus session storage. Of like, is there a particular reason you'd want to pick one over the other, or are they fairly comparable?
So local storage, the lifespan of local storage is actually longer, meaning that session storage, if you store something there and you close a tab, it disappears forever. But local storage, it actually persists across, even if you like restarted the browser, unless you explicitly clear it. So that would be the reason why.
Okay. Thank you.
Good question. Yay, more questions. Thank you for asking questions, by the way.
Hello, thanks for the talk. I tried around with this stuff a little bit earlier, and it was not possible to do something like that on a static site, because the server had to send a header for the web worker to allow storing the SQLite, basically. Is this still the case, or is there a workaround for that?
Yes, so to use OPFS, depending on where you use it, there are some HTTP headers that you have to use. I believe that's a question. And you have to set those up as part of your web app and the infra that serves it, basically. And so that is still the case. That is not a room-specific thing. It's really because OPFS needs those headers. But it also depends on how exactly that web worker is. So using SQLite WASM on a web worker will require some of those headers. I believe SQL.js might not require them, depending on how you use it. For example, if it's an in-memory database and you don't persist it. So that's dependent on that web worker side of things. Some might need those HTTP headers and others don't. I believe we are lacking a little bit of documentation on that, so something for us to improve. Does that answer your question?
Yeah, thank you.
Thank you. Thank you for asking it. Oof, that was a hard one. Any other questions? All right, thank you so much.
Thank you.